Out on the open ocean, some of the biggest dangers aren't the storms you can see coming. They're the invisible forces you can't. So today, we're going to talk about one of the most counterintuitive principles in naval architecture, something called the free surface effect. Let's dive in and uncover the physics behind this pretty serious hidden danger. So let's start with a question that seems to completely defy logic, right? I mean, less weight should be safer, shouldn't it? But as we're about to find out, when you're talking about liquid inside a moving ship, that assumption, well, it can be catastrophic. And that question, that's really the key to this whole thing. Okay, so to get to the bottom of that question, we first need to meet the main culprit behind this hidden danger. And it all starts with one simple concept, the slack tank. So what is a slack tank? It's really any tank on a ship that's only partially full. See, if a tank is totally full of liquid, it's basically like a solid block of cargo. It doesn't move. Same thing if it's completely empty, of course. The danger only, and I mean only, pops up when there's space for that liquid to move around, when the tank is slack. And this, right here, shows you the problem perfectly. On the left, the ship's upright, everything's fine. But look at the right. As the ship starts to roll or heel over, check out how that entire mass of water just surges to the low side. That's not what a solid weight does. This shifting liquid creates a dynamic and really dangerous imbalance. And that movement, it's not just passively sloshing around. It's actively fighting the ship. Every single time the ship tries to right itself and get back to being upright, that mass of water rushes to the low side, basically pushing against the ship's natural stability. So you've got this hidden force, and it's actively working against the ship's safety. So how in the world does this sloshing actually make a massive ship unstable? Well, the answer is in this fascinating, almost deceptive bit of physics that has some very, very real consequences. It's kind of like a magic trick. Okay, to get this, we got to do a super quick dive into the basics of ship stability. You've got three main players. G, that's the ship's center of gravity, and the golden rule is you always want to keep G as low as possible. B is the center of buoyancy, that's the upward push from the water, and M is the metacenter. All you really need to know is that the distance between G and M, that's your stability margin. The bigger that distance, the safer the ship is. And here it is. This is the big reveal, the magic trick. The free surface effect doesn't actually add any weight to the ship, but what it does is create an effective change. The physics of it all works out as if the ship's center of gravity, G, has been physically lifted up to this new, much higher and much more dangerous point. We call it GV for virtual G. And look, this diagram shows it perfectly. You see the original, safe center of gravity down there at G? But because of that sloshing liquid, the entire ship now behaves as if its center of gravity is way up at GV. That distance it moved up, that's a direct hit to the ship's stability margin. It's what's called a virtual loss of GM. And this is the most important thing to get. This virtual change has a very real, very dangerous effect. Every single inch of that stability margin that gets lost makes the ship that much less stable and that much more vulnerable to capsizing. But it gets worse. See, the danger from this effect doesn't just add up, it multiplies. And the way it multiplies is what makes this whole thing so incredibly hazardous. Okay, now don't worry, you don't need to memorize this formula, but I want you to look at just one part of it. See the breadth? That's the width of the tank. And how it's cubed? That little number 3? That is the key to why this whole thing is so incredibly dangerous. And this leads to what we call the B cubed rule. And honestly, it is staggering. If you double a tank's length, the free surface effect gets twice as bad. Okay, that makes sense. But if you double the width of that same tank, the effect doesn't double. It multiplies by a factor of 8. It's 8 times worse. That's why wide, open tanks are an absolute nightmare for stability. Okay, so what about the amount of liquid? Here's a classic question that trips a lot of people up. Which of these is more dangerous? A tank that's half full with 5 meters of water, or a tank that has just a shallow 10-centimeter puddle sloshing across the bottom? And the answer, which is pretty mind-blowing, is that the effect is identical. It's exactly the same. That formula only cares about the surface area of the liquid that's free to move, the length, and most importantly, the width. So whether it's a few inches deep or a few yards deep makes absolutely no difference. As long as it can slosh, the danger is the same. So, knowing all this, knowing how unbelievably dangerous this effect can be, how do ship designers and the people sailing these ships actually manage to tame this hidden force? Well, the worst case scenario you have to avoid is something called an angle of lull. This is what happens when the free surface effect is so bad that the ship's stability actually drops below zero. The ship will just flop over to one side and get stuck there. It can't right itself, it's incredibly unstable, and at that point, just a strong gust of wind or a single wave could be the final push that capsizes it. So, the number one solution is just smart design. Because of that crazy B cubed rule we talked about, designers almost never build a single wide tank that stretches across the whole ship. Instead, they put a solid wall, a longitudinal bulkhead, right down the middle, splitting it into two much narrower tanks. And by cutting the width in half, you don't just have the danger, you reduce the total effect to just 1/4 of what it would have been. But what if you're already in that dangerous situation and an angle of lull? The recovery procedure is critical, and it's very specific. First, you do anything you can to lower the ship's center of gravity. If you have to add water, you must start filling a tank on the low side. Now, this sounds completely crazy, right? Because the ship will actually heel over even more at first, which has got to be terrifying. But if you add weight to the high side, you're just raising the center of gravity even more, and you risk a full capsize. And this all leads us to the single most important rule for any officer on that ship's bridge. You don't guess. You don't eyeball it. You calculate. Every single action you take to correct stability has to be carefully planned out, because the wrong move, no matter how good your intentions are, could literally be the last move you ever make. The free surface effect is just this powerful reminder that in really complex systems, the most dangerous threats are often the ones that just don't make sense to our intuition. It really makes you wonder, doesn't it? What other hidden forces, what other invisible principles are at play in the technology and the structures we depend on every single day, just waiting for the right conditions to show up?